So we'll go through the final chapter, and little text. Looking at the one-line diagram, which is important in any facility to have a one-line diagram that's updated. Anytime this change is done, they need to be brought up to date so that if there's an emergency fix or new work that's going to be done, we go back and look at drawings of any type, schematics, one-line diagrams. If they haven't been constantly updated, you're working with information on previous versions, so it's going to waste time, might cause problems if you don't have the right information. The one-line diagram that we'll look at for the college, you'll use it in your research project. Follow through and show where the panel is in room PV016. So the main function of a power distribution system is to provide electrical power for whatever need in a safe and dependable manner. This is accomplished by using a variety of electrical equipment, such as transformers, switchgear, breakers, motor control centers, and emergency generators. To provide a reliable source of power, most modern plants use a dual supply system for power distribution. A dual supply system is one in which two independent power lines are used to supply the same load. This dual system is used from the inlet of the main source of power to up and including the end users. So figure 1 is this one-line diagram here, which is easier in your textbook probably to look at the same time as it's being described. The power is supplied from two separate on-site electrical generators, which are producing power at 13.8 kV or 13,800 volts. There is also an external backup power source being supplied at 13,800 volts, which when required is transformed down to 138,000 volts, which when required is transformed down to 13,800 volts. So if you're looking at the diagram, there at the very top is the alternate external supply, 138,000 volts. If it's needed, these two generators are the main source, generating at 13,800 volts here. If for some reason these aren't available, the external supply is available and transformed here to here to 13,800 volts. So the main power is supplied by the two on-site generators. This is then separated into two individual power lines or buses. Bus is used as a description of an electrical conductor in big power panels. The bus bars are where breakers are passed on to. The two buses are identified in figure 1 as A bus and B bus. So from each of the generators, there's A bus coming down here and B bus coming down here. The 15 kV main feeder breakers identified as 1101 and 1102 supply the 13.8 to 4160 volt 10 megavolt amp power transformers PTR 101 and PTR 102. So if we look at it again, these breakers then, each of these separately, are 13.8 kV breakers which are then feeding to the two power transformers, which are dropping the voltage down to 5 kV. This is where the power is reduced in voltage from 13.8 kV to 4.16 kV through the use of step-down transformers. This 4.16 kV power is then fed to the 5 kV incoming switchgear breakers 11201, 11202. These two 5 kV switchgear breakers together with the tiebreaker 11203 make up the first level of automatic power transfer. So now we're looking down the two 5 kV switchgear breakers, and the tiebreaker switchgear is here. Under normal operation, both incoming breakers 11201 and 11202 are closed, and the tiebreaker is open. When one of the incoming breakers loses its power supply, that breaker will open, and the tiebreaker will then close, re-establishing power through the other breaker. This 5 kV is also supplied to high voltage motors in the plant. The power from the 4160 volt transformer then feeds the 4160 feeder breakers. 4.16 kV power is also supplied to MCC number 1, which is motor control center number 1, to provide power for the 4160 volt boiler feed and cooling water pumps. So if we're looking here now, if one of these breakers fails or is open for some reason, so you don't have both A bus and B bus feeding, normally these are closed, so there is power feeding through both of them, and this is the tiebreaker that is open, separating the two. If one of these is open for some reason, you lose power, this tiebreaker switchgear will close so that this side will feed all the way across here. If this tiebreaker was open, A bus would feed down all the left side over here, B bus would feed down in here and all the right hand side. So you have the option of having either A or B feeding everything here. Then your 4160 volt MCC switchgear here, motor control center number 1, and you'll have a breaker for a disconnect for boiler feed pump and the cooling water feed pump. So both of those pumps are 4160 volts. Feeder breakers 11211 and 11212 supply the 3 megavolt amp 4160 volt to 480 volt power transformers PTR 211 and PTR 212. Feeder breakers 11221 and 11222 supply the 2 megavolt amp 4160 volt to 480 volt power transformers, and PTR 221 and PTR 222, which in turn supplies substation number 1. Now we're down. 11221 is here, and it needs this transformer, PTR 221, 4160 volt, 480 volt, 2 megavolt amps. So it's step down transformer, and that goes to substation number 1. Feeder breaker 11211 then feeds PTR power transformer 211. It's also 4160 volt, 480 volt step down, and it's rated at 3 megavolt amps. 11212, 11222 feeder breakers are each feeding the 4160, 480 volt power transformers over here also. And this one also feeds substation number 1, as does this one. So you have either of those two can feed to substation number 1. And this one continues down to the next drawing. So we can finish up here. The two other feeder breakers, 11231, 11232, also receive power from the main 4160 volt supply. These two 5 kilovolt switchgear breakers and the tie breaker, 11233, make up the second level of automatic power transfer. This system supplies power to critical 4160 volt motor drivers. So they were 11231 to 11232. Turn the next row. Alright. 312, 311. 231 is here. So this is where the 4160 volt emergency motor control center, and you've got a 900 kilowatt natural gas turbine generator here. So this natural gas generator is able to feed into the system here if power is lost back here and you don't have the access to the other bus, like closing the switch gear. So you do have emergency power backup generator here, which now there's 3 generators involved. The 2 main ones for power supply and emergency backup. So we get to figure 2, 4160 volt power from power transformer 211 and 212 supply feeder breakers 11301 and 302. These feeder breakers, together with the tie breaker 11303, make up the third level of automatic power transfer. And this system provides power to many 480 kV users. So feeder breakers 11301, 302 are coming from these 2 feeders here. So they're 480 volts on the secondary side of those transformers. So your 480 volts here. Again, you've got the option of a tie breaker so that either one of these buses can feed this system down here, where you have motor control center here, 480 volt 12208 transformer, and you've got a lighting panel and 120 volt and 280 volt distribution panels down here. MCC2 here would be for strictly 480 volt use. So down here again, you've got another backup generator, 480 volt emergency backup generator. Diesel instead of natural gas this time is 250 kilowatts. And these automatic ATS, automatic transfer switches, will operate in the event of power outage back here. They'll sense that the power isn't coming from the 480 volt supply above, and they'll set the generator into transfer sequence, where it'll start the generator, let it warm up, and then automatically open. It'll close from here over there, and this line here will switch over to here. So in the event that incoming utility power should be lost, critical users are supplied with 480 volt emergency power from a 250 kilowatt diesel generator. The operation of the automatic transfer switches, ATS3 and ATS4, function the same manner as the automatic transfer switches described above for the 4160 emergency board control center system. So everything is set up in this system that it's almost impossible to be without power. It would be pretty critical if we didn't have access to power or something. This diagram, together with the one above, will be on the final test. So go through it, read through it, so you understand the different components and what can be, what power can be transferred, the different generators and where they sit in the system. I'll have this diagram on the test and about 5 questions. Just about information that is on there, you just have to go through and pick it out and answer the questions. We're talking about backup generators. All of this information has to be accessible to check on the operation of that generator. So the following is a description to the unit shown in Figure 3, which consists of a steam turbine coupled to an AC generator. Generator is rated at 250 kilowatts, 600 volts, AC, 60 hertz. So on the control panel, first, kilowatt hours meter. It's a meter that measures and records the amount of power produced by the generator. The kilowatt hour is a kilowatt of power used for 1 hour. Exciter field voltage. This gives an indication of the DC voltage that's being supplied to the generator field windings. Exciter field current gives an indication of the DC current that's being supplied to the generator's field windings. AC kilowatts is an indication of AC kilowatts that the generator is producing. So we've got kilowatt hour needed. On this diagram, it's hard to distinguish which ones are which. The number is the same here. We've got 1 is a kilowatt hour meter. We've got 2 exciter field voltage, 3 is exciter field current. So this is voltage, DC current, and then number 4, AC kilowatts. Number 5, A, B, and C phases are indication of the AC current expressed in amps or amperes, which is being produced by the 3-phase generator. So you can look at these 3 ammeters, 1 for each phase. So there'll be an ammeter will have a current transformer with a conductor passing through it, seeing that magnetic field, and showing you on this ammeter how many amps are being used on each of the phases. If you look on these 3, phase A and phase B are pretty close to being the same. Phase C is a lot lower. In a 3-phase system, you want to try and keep those 3 phases balanced as much as possible. 6, voltage adjust, which is used to adjust generators' excitation voltage, which in turn will adjust the output voltage. When you did the AC alternator lab, you saw where adjusting the DC excitation affected the output voltage of the alternator. Frequency is an indication of the frequency of the power being produced by the generator. It's expressed in hertz, and you want to make sure that stays at 60 hertz. Power factor is a meter that's used to check the power factor of the generation system. So that ideally you want 90% or better power factor. Poor power factor puts pressure on the generation system. So you monitor it, see if there's some way of correcting it with capacitors or the motor that you can use as power factor correction. Synchronous motor, when it's used to correct power factor, is called a synchronous generator. A is your power factor here. AC volts, in the case of the AC voltage, is expressed in volts, which is being produced by the three-phase generator. AC kilobars is a measurement of the reactive power being generated by the AC generation system, which would be directly related to your power factor. Voltmeter selector is used to check voltage on each phase of the generator. So 11, you've got 3 selections here. This will be A to B, will be here, so you can check the voltage from phase A to phase B. If you switch it to where it is right now, it's between phase A and phase C, and the third one will be looking at the voltage between phase B and C. This control panel is all analog meters and hardwired. New systems will have a much more electronic touchscreen. Probably you can scroll through all of the information you need to find on a newer type panel. Let's stop it. I've got some fuses and stuff to grab. So still talking about generators. The protection of generators involves a consideration of more possible abnormal operating conditions than the protection of any other system element. In unintended power stations, automatic protection against all harmful abnormal conditions provided. So protection. In the form of fuses. A fuse is the simplest form of automatic overcurrent protection that has a circuit opening fusible link directly heated and destroyed by the passage of the overload current through it. The link is so sized that the heat created by the normal flow of current through it is not sufficient to fuse or melt the metal. And I have an older style cartridge fuse that if you take it apart, it has a replaceable fuse link. That on the fuse link here, one connection point of the fuse is on the first top end, the bottom end is the other part of the fuse. Inside is this fusible link that will melt if there is too much heat or if it's designed for a short circuit, it will open also. The insulating part over here holds the fusible link, so the conductor part of the fuse is from the top through the fusible link and down to the bottom. And the nuts on the face would be where you could replace that fusible link of this fused loop. There's different sizes, types, styles of fuses, depending on the voltage, the current, the class of the fuses, depending on the use. There are many different styles. This is a 600 volt, 400 amp fuse on your standard 60 amp, 250 volt cartridge fuse. You see it in an older fuse panel in a residence. This one, fusible link is 200 amp, 250 volt. Cartridge fuses are used on circuits 125 volts or less to ground, typically residence. Maximum continuous current carrying capacity of a plug fuse is 30 amps, and commonly used standard sizes are 10, 15, 20, 25, and 30 amps. These fuses do not have published interrupting capacities since they are ordinarily used on circuits that have relatively low values of available short circuit current. They don't really describe short circuit current here, but it's an important part of fuse information depending on the proximity to a transformer. If there is a short circuit phase to phase, the amount of available short circuit current at that instant can be in the tens of thousands of volts. So you have to make sure that in the application where the fuse is, the interrupting rating matches the system. Cartridge fuses are used on circuits with voltage ratings up to 600 volts. The standard voltage ratings of these fuses being 250 and 600 volts. The non-renewable cartridge fuse is constructed with a zinc or alloy fusible element enclosed in a cylindrical fiber tube. The ends of the fusible element are attached to metallic contact pieces at the end of the tube, which is filled with an insulating porous powder. On overloads or short circuits, the fusible element is heated to a high temperature, causing it to vaporize. The powder in the fuse cartridge cools and condenses the vapor and quenches the arc, thereby interrupting the flow of current. So again, these are pictures of the fuses that I have. You'll have seen, if you've seen a fuse panel in a house, the 15 amp plug fuse that screws in. The cartridge fuses, again, will come in different configurations. This style here is what you'd see in a 600 volt fuse up to 30 amps. Once you get above 30 amps, you'll see it with the post on the top and bottom, so that you can't put a higher rated fuse and a lower rated disconnect. Cartridge fuses, both in 250 volt and 600 volt ratings, are made to fit standardized fuse clips. These sizes are 30, 60, 100, 200, 400, and 600 amp sizes. Each fuse clip size has several continuous ratings of 70, 80, 90, 100 amps. Time lag fuses are made in both the plug and cartridge fuses. These fuses are constructed so as to have a much greater time lag than ordinary fuses, especially for overload currents. They do operate, however, to clear short circuit currents in about the same time as do other fuses. Time delay fuses are used more in motor circuits to allow for the high current from the startup. Time lag fuses have two parts, a thermal cutout part and a fuse link. The thermal cutout, with its long time lag, operates on overload currents up to about 500% of normal current. Currents above this value are interrupted by the fuse link. Time lag fuses find their greatest application in motor circuits, where it is desirable that the fuse provide protection for the circuit and yet not operate because of a momentary high current during the startup period of the motor. High voltage fuses are used for protection of circuits and equipment with voltage ratings above 600 volts. Two of the commonly used fuses are shown here. 5A on the left shows an expulsion fuse, which consists of a fusible element mounted in a fuse tube and depends on the pressure built up in the fiber tube when the metal melts to blow the gases out of the open end. This takes with it the bottom section of the fuse link and establishes a gap between the two contacts. Figure 5B on the right shows a liquid-filled fuse in which the arc is quenched by the liquid. The action is similar to that in an oil immersed switch. The spring is normally held in tension by a high-resistance tension wire. This wire is parallel by the fuse wire that carries the current. When high current melts the fuse wire, the tension wire immediately melts and releases the spring, which then contracts and pulls the contacts apart. Similar to these would be what you would see on a utility pole. The fuse holder is a C-shaped bracket with the conductor on each end of it. The fuse would go in the middle, making it look like a D shape as opposed to a C when the fuse is in there and working. When the fuse blows, there's a hinge on the bottom of the fuse holder. When the fuse blows, it drops out, and you can visually see that the fuse holder is open, so the fuse has blown. A safety switch is a device for isolating parts of an electric circuit or for changing connections in a circuit or system. When a switch is mounted in a metal enclosure and is operable by means of an external handle, this is called a safety switch. The switch itself is not designed for interrupting the flow of short circuit currents. However, switches and fuses are often incorporated into a single device called a fusible safety switch, shown here. This is a very old picture of a switch. But the fuses are bolted on top and bottom to each one of these fuse holders. When this switch is closed, these prongs of the fuse holder will go in here and complete each of the three phases in this circuit. Safety switches are made in 2, 3, 4, and 5 pole assemblies, which means the number of conductors that it's opening or closing, and they can be either fused or non-fused. They are made in single throw and double throw units, and depending on their use, they have a variety of constructional features. One type, known as type A, has a quick break mechanism so arranged that regardless of the speed at which the operating handle is moved, a spring-loaded arrangement causes the contacts to open or close with a quick motion. This type of switch also has a door interlock to prevent the opening of the enclosure door when the switch is closed. The reason for the quick operation, quick make, quick break, is to reduce the amount of arcing. If you take a disconnect and move the handle slowly, then you're causing actually welding in that switch. So if it's spring-loaded, it bangs open and bangs closed, and the least amount of arcing possible if it's used under load. Enclosed switches, either fusible or non-fusible, are used as disconnecting devices for many services in buildings, for feeder and branch circuit protective and switching devices, and for motor protection and switching. Safety switches are available in 2 voltage ratings, 230 volts and 575 volts AC. Current ratings are the same as for standard fuse clip sizes. Circuit breakers are an automatic device that open under abnormally high current conditions. In 3-phase systems, circuit breakers can open all 3 hot lines when an overload occurs. They are designed so that they will automatically open when a high current occurs, which exceeds the rating of the breaker. Most circuit breakers employ either a thermal or a magnetic tripping element. They may also be activated by remote control relays. Relay systems may cause circuit breakers to open due to changes in frequency, voltage, or current. The internal construction of a circuit breaker is shown here. This is a residential type breaker. In most cases, the circuit breakers must be reset manually. So if that breaker trips for an overcurrent or a short circuit, they'll go to a position between on and off. And usually in order, if it is tripped, the switch has to be switched all the way to the off position and then back to the on position. Anytime a breaker trips, find out why. Don't just turn the breaker back on again. If there's been a short circuit in a fuse, it destroys the fuse, and you have to replace it. If it's a short circuit in a breaker, it's possibly done some damage, and if you keep resetting it and trying to make it without checking the problem, you are definitely damaging the breaker. Circuit protection relays. Modern alternators consist of a stator on which the alternating current voltage producing windings are installed. It also contains a rotating armature or rotor on which a DC excitation winding is placed. When a synchronous generator loses excitation, the rotor accelerates and operates as an induction generator running above synchronous speed. As a result, the machine draws inductive reactive power from the system instead of supplying it to the system. Heavy currents are induced in the rotor teeth and wedges and can cause thermal damage to the machine if it continues to operate. Round rotor generators are not suited to such operation because they do not have windings that can carry induced rotor currents. This device detects the loss of excitation on the generator. It includes 2 MHO characteristics looking at the generator, each with adjustable reach, offset, and time delay. MHO is a unit of measurement of electrical conductance, which is backwards for ohm for resistance. Overexcitation, when the ratio of the voltage to frequency exceeds a set value for a given generator, severe overheating could occur due to saturation of the magnetic core of the generator and the subsequent inducement of stray flux in components not designed to carry flux. Such overexcitation most often occurs during startup or shutdown while the unit is operating at reduced frequency, or during complete load rejection, which leaves transmission lines connected to the generator station. Failure in the excitation system can also cause overexcitation. A volts per hertz relay with an inverse time characteristic that matches the capabilities of protected equipment and with definite time set points is used to protect the generator from overexcitation. Another type is loss of synchronism. When 2 areas of power systems or 2 interconnecting systems lose synchronism, there will be large variations in voltages and currents throughout the systems. The voltages will be maximum and the currents minimum when the systems are in phase. The voltages will be minimum at the currents maximum when the systems are 180 degrees out of phase. The The resulting high peak currents and off-frequency operation may cause winding stresses, pulsating torques, and mechanical resonances that are potentially damaging to the turbine generator. Therefore, to minimize the possibility of damage, a unit should be tripped without delay. Unbalanced faults and other system conditions can be unbalanced three-phase currents in the generator. The negative sequence components of these currents can double frequency currents in the rotor that can lead to overheating and damage. The negative sequence overcurrent function relay is provided to protect the unit before the specified limit for the machine is reached. And that's probably really old too. Under voltage protection, over voltage protection, reversal of power. For generators operating with another generator, it's imperative that the power direction be supervised. If the prime mover fails, the alternator operates as a motor and drives the prime mover. A relay detects the reversal of power direction and switches off the alternator. Power losses and damage to the prime mover are avoided. Dead generator energization protection. If a dead generator is accidentally energized while on turning heater, it will start to behave as an induction motor. During the time the generator is accelerating, very high currents are induced in the rotor and it may be damaged very quickly. Protection is usually provided by 3 directional inverse time overcurrent relays, one in each phase connected to operate for reverse power flow in the generator. Overfrequency. Faults in the system can result in a system breakup into islands, which leaves an imbalance between available generation and load. This results in an excess of power for the connected loads. Excess power results in an overfrequency condition with a possible overvoltage from reduced load demands. Full or partial load rejection can lead to overspeed of the generator, therefore overfrequency operation. In general, overfrequency operation does not pose any serious overheating problem unless the rated power and about 105% voltage are exceeded. Control action can be taken to reduce the generator speed and frequency to normal without tripping the generator. When sufficient power is being generated for the connected load, underfrequency results with a heavy load demand. The drop in voltage causes the voltage regulator to increase the excitation, which results in overheating in both the stator and the rotor. At the same time, more power is being demanded, with the generator less able to supply it at reduced frequency. Prolonged operation of a generator at reduced frequencies can cause particular problems for gas or steam turbine generators, which are susceptible to damage from operations outside their normal frequency band. The turbine is more resistant than the generator at reduced frequencies because of possible mechanical resonance in many stages of the turbine. If the generator is close to the natural frequency of any of the blades, there will be an increased vibration, which can lead to cracking of the blade structure. While load shedding is primary protection against generator overloading, under-frequency relays should be provided to provide additional protection. Although a single field ground fault will not affect the operation of a generator or produce any immediate damaging effects, the first ground fault establishes a ground reference, thereby making a second ground fault more likely. This will increase the stress to ground at other points of the field. A second ground fault will cause extensive damage by shorting of parts of the field winding, causing high unit vibrations, causing rotor heating from unbalanced currents, and arc damage at the points of the fault. A field ground relay is installed, which must reliably detect the first ground fault. This will allow action to be taken either through the tripping of the unit or an operator alarm. This is to avoid continued field winding insulation deterioration that would cause a second ground fault and major One of the main causes of ground fault is insulation failure. Zero sequence impedance of a generator is usually lower than the positive or negative sequence impedance. Therefore, for a solidly grounded generator, the single phase to ground fault current is greater than the three-phase fault current. Generators are usually grounded through an impedance to limit the ground fault current. The fault current available for sensing a phase to ground fault on an impedance grounded generator can be very small compared to phase-to-phase faults. Depending on the location of the fault and the method of grounding the generator, separate ground fault protection is usually provided. Stator overheating protection. This problem is caused by overloading or by failure of the cooling system. Overheating because of short circuit laminations is very localized, and it's just a matter of chance whether it can be detected before serious damage is done. The practice is to embed resistance temperature detector coils, RTDs, or thermocouples in the slots with the stator windings of generators larger than 500 to 1000 kVA. You got figure 9 in your book. It's not showing video. It says something to the board.
Yeah, some picture skills.
So figure 9 shows the bridge circuits employed by the RTDs. Enough of the detectors are located at different places in the windings so that an indication can be obtained of the temperature conditions throughout the stator. Primary protection for generator phase-to-phase faults is best provided by a differential relay. Differential relays will detect phase-to-phase faults, three-phase faults, and double phase-to-ground faults. With low impedance grounding of the generator, some single phase-to-ground faults can also be detected. A type of non-automatic bus switchover unit, shown in figure 10, operates in the following manner. Here's the figure 10. Okay. So this would be the procedure that would happen in the previous diagram showing the generators and tiebreakers. Under normal circumstances, when utility power is available, the utility power runs through the transfer switch, control contactors, the power is connected to the distribution panel and then to the electrical loads. A battery charger installed in the transfer switch control is powered by the utility to keep the starting battery in the generator set charged. When utility power fails to less than 85% of its normal value, or it fails entirely, the standby power system will automatically go through a start sequence. The transfer switch control circuitry constantly monitors the power quality from both the utility source and the generator set. When the transfer switch control circuitry senses the unacceptable utility power, the control waits for 3 seconds and then sends a signal to the start the generator set engine. If utility power returns before the 3 seconds have passed, the generator set will not be signaled to start. When the start signal is received and providing the manual auto switch is set to auto, the engine starts, reaches the proper operating speed, and AC power is available at the generator set. The transfer switch control circuitry senses this, waits for 3 seconds, and then will transfer the generator set power to the transfer switch contactors. The sequence of operation usually occurs in less than 10 seconds from the time the power outage occurred to the time when generator set power is connected. The transfer switch includes a manually operated handle. If the transfer circuitry does not cause the automatic transfer to generated power, the manual auto switch can be moved to the manual position and the handle then used to transfer from utility power to emergency power or vice versa. When utility power comes back on, the transfer switch control circuitry senses this and will watch for acceptable voltage levels for a period of 5 minutes. After this 5-minute period and the voltage levels have been stable, the control will signal the transfer switch contactors to retransfer the load back to utility power source and then disconnect the generator set source. At this point, the generator set is offline and will be operated automatically another 5 minutes to allow it to properly cool down. After this cool down cycle, the generator set will be automatically shut down and reset to standby mode. A ground is defined as a reference point of 0 voltage potential, which is usually an actual connection to the ground of the earth. The need for grounding is very important in that an open ground condition could present severe safety problems to anyone operating the power generation equipment. Grounding assures that any person who touches any of the metal parts will not receive a high voltage electrical shock. The conductor which is used for this purpose is either a bare wire or a green insulated wire, and it will be copper. Lightning arresters are used to cause the conduction to ground of excessively high voltages that are caused by lightning strikes or other system problems. Power lines and associated equipment could become inoperable when struck by lightning. They are designed to operate rapidly and repeatedly if necessary. Lightning arresters are connected to transformers for the insides of switchgear. Here, the lightning arrestor is used by the path to ground for lightning strikes or hits. You'll see similar shaped devices, lightning arresters on utility poles. The UPS, uninterruptible power supply. An uninterruptible power supply is required for plant systems that cannot tolerate a momentary loss of voltage and/or frequency. The purpose of this type of system is to provide a bumpless supply of electrical energy to critical plant control and shutdown circuitry. The term bumpless means that when the normal supply of utility power is interrupted, power is always maintained to the users by backup sources such as batteries and generators. This would include plant computers, control systems, plant lighting, and compressor trip solenoid belts. Components of the UPS system: rectifier. This unit converts 600 volt 3-phase AC power to 220 volts DC, which provides power to charge the batteries and also supply the inverter. The battery bank is used to store electrical energy and supply the inverter in the event of a loss of AC power. The inverter converts 220 volt AC power from the inverter to 120 volts single phase AC for critical plant AC power users to maintain a supply of stable voltage and frequency output power.
To the inverter, I read that diagram. It converts 220 volts DC power from the inverter. And there's an inverter. The next one. The inverter.
Converter will take AC to DC. An inverter will take DC and change it to AC.
So that part of that, saying that converts 220.
Well, it's usually the word converts. It should be saying changing. It's changing 220 volt DC power from the inverter to 120 volts AC.
So the inverter is doing that.
An inverter will take DC and change it to AC.
Yeah, I understand that now. I'm trying to make sense of that.
Well, I think they used the wrong word when they said converts.
Alright. They say it changes. Let's say it changes, right?
Yeah.
It changes 220 volt DC power from the inverter. So I'm saying, are they talking about the inverter or the rectifier?
Same thing. An inverter is a rectifier. When we talk a bit about variable frequency drives. Variable frequency drives take AC, change it to DC internally, and then that DC gets changed back to AC for the motor. Yeah. And a variable frequency drive is called an inverter. It is called all kinds of names that are sort of all thrown into the same.
So if that we are talking right there, we are talking about inverters.
The inverter takes 220 volts DC and provides you with AC.
I'm saying, why are they saying inverter takes the power from the inverter? That's part I'm trying to understand.
The inverter converts 220 volts DC from the batteries.
Yeah, but because they are from the inverter. In other words, they're saying the inverter converts 220 volts DC power from the inverter.
Yeah, simply from the batteries to 120 volts. Because the battery bank, the rectifier takes 600 volt 3 phase and changes it to 220 volt DC to charge the batteries.
Yes.
The battery voltage is 220 volt DC. So when it's needed, the 220 volt DC from the batteries is changed to 120 volt AC by the inverter. A static switch, 120 volts, single phase AC power from the inverter is fed through the static switch to the 120 volt critical users. If the inverter should fail for whatever reason, the control system will automatically open the switch located upstream of the rectifier and close the switch on the alternate 600 volt feed. This 600 volt power will then be reduced to 120 volt single phase AC through the use of a step-down transformer. The static switch will also switch over to this alternate supply source. This all occurs within 1/240th of a second, or a quarter of a second. So the UPS system operation. Utility power at 600 volts AC is supplied to the rectifier charger section from the motor control center. The rectifier charger converts the 600 volts AC to 125 volts DC. This 125 volt DC is used to supply power to critical control circuitry and also maintain the battery banks in a fully charged condition. This 125 volts DC power output from the rectifier charger also goes to the inverter, where it is converted back to alternating current. This 120 volt AC single phase power passes through the bypass switch to supply the various AC power users. If there's a loss of the utility power, the DC and AC users will then be supplied with power from the battery banks. This will be until the automatic transfer switch starts the emergency generator, and the generator will then supply the power to the UPS system. If the inverter should fail, the bypass power will automatically be selected to supply AC UPS users. The bypass switch is a make before break type of switch to provide a bumpless transfer of power. An alarm will enunciate to alert the operator of a UPS trouble if there is a loss of utility power while the inverter is on bypass. Circuitry in the automatic transfer switch will not allow it to transfer back to normal or utility power when it becomes available. This interlock ensures a bumpless transfer of power to the AC UPS users by employing a time-delayed restoration of normal power 60 seconds after the inverter has been placed back in service. Whenever the inverter is on bypass and there's a temporary loss of normal or utility power to the UPS system from the MCC, then the 120 volt AC circuits will be lost until power has been restored to the MCC, either from the utility or generator starts. And all this is dependent on the ability of the batteries to keep that power on. What are we at? 10:20? 10:30, we're going to go look at the college electrical. The duration of time for which the batteries can perform their function will depend on their ampere hour rating and the current drawn by the various DC circuits and the inverter. If the power draw is normal, and providing that the batteries are in good condition and fully charged, they should provide adequate power for approximately 4 hours. The batteries for this application use the same design as all lead acid batteries. So the sulfuric acid electrolyte has been immobilized in a microporous absorbent medium, leaving no free liquid acid in the battery cases. The individual cases are sealed with rupture protection provided by a relief valve, which opens at 41.3 kPa and resets between 50 to 20 kPa. Under normal operating conditions, the battery should not leak or vent hydrogen and acid mist during recharging. Battery maintenance. Testing the battery should be done anywhere from 1 to 4 times each year. Recording of the voltages at the time of each inspection should be performed. The completion of a load test should be done 4 times per year. A visual inspection should be completed during each scheduled maintenance. This visual inspection should include the possibility of any signs of cracks, leaks, swelling, or corrosion of the battery cases taking place. Another important part of the visual inspection is to make sure that there is sufficient space between each battery. This air gap will allow heat to escape. All connections must be torqued each year to maintain a tight connection. It is important to follow the manufacturer's specified torque values. If the connection is too loose, it could overheat during a discharge and cause problems. If it's too tight, the post or terminal could be distorted. The exterior battery should be cleaned with a damp cloth. You may need to use a damp cloth with a mixture of a neutralizer to remove any acid film. Corrosion should be brushed away with either a stainless steel brush or a brass brush. The installation date of each battery should be recorded. A clear and accurate log of all the findings from each maintenance period should be maintained. Let's take a break and I'll find Phil. Safety. Safe working habits are largely a matter of common sense. Power plant operators should be aware of the possible danger to themselves and others when operating electrical equipment. Quite often, an operator must report electrical malfunction and take equipment out of service for maintenance by qualified personnel. When a power plant engineer is involved in plant design, safety of equipment and personnel is of vital importance. Attention should be placed on the following. Electrical installations. All motors, generators, and equipment should be installed in such a way that no live parts are exposed. Sufficient space must be allowed around equipment for inspection and repair to be carried out safely. Guards must be adequately covered. All rotating parts. Identify all feeders and circuits as to their purpose so that correct circuit breakers and switchgear can be observed easily at the breaker panel. So that's all part of keeping diagrams, labeling of panels, all schematics updated so that everything is as safe as possible. Comfortable but close-fitting clothing should be worn. Wearing of insulated safety shoes is recommended when working on electrical equipment. Avoid wearing any loose articles such as rings and chains that may come in contact with light equipment. When working on live equipment, consider all circuits to be live unless one is certain that they are dead and cannot, by some human error, be made live. Lockout and tagging. Place tags that show equipment is out of service for maintenance when opening an electrical circuit. The tag should bear the name of the person who put it there and should only be removed by this person and the switch be closed by that person. An operator should isolate all equipment, such as pumps, before maintenance is started. All switches must be locked open at the power source. Test the equipment after isolation by attempting to start it at the start-stop stations. The circuit may be open but charge capacitors and injure a person. Always open switches completely before removing fuses. If it is necessary to change a fuse in a live circuit, don't. This is the part of this chapter that's very wrong. Never change a fuse in a live circuit. Just ignore that part. It should never happen. Switches should be open in a firm, positive manner to prevent arcing, like the fast make, fast break. The spring action. All portable electric tools should be properly grounded. Portable electric tools that are mostly rechargeable now, but if you have electric portable tools, if they don't have a three-cable cord, it must say on them that it's double insulated. Fire hazards. Due to conductive nature of water, it should never be used on any electrically generated fire. Likewise, electrical equipment is in the area of a fire, and water is the appropriate fighting medium. Isolate the equipment before attempting any probes. Just use the right fire extinguisher. And we do questions in there to give you some